Okay, let's go for take three. Hello and welcome to Cup of Cosmology. My name is Diana Hooper, Charlie to friends. I'm a theoretical physicist currently doing a postdoc over at the Helsinki Institute of Physics in the University of Helsinki, Finland, and I'm a cosmologist. So that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. It's a great topic. I love being a scientist and I love chatting to everybody about all of the cool things that I get to study in the universe. For anyone who doesn't know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want, and I will do my best to try to answer. We are having many technical issues today. I started the stream as scheduled half an hour ago. The stream just died randomly, and I got the pop-up immediately saying you've gone offline, so I wasn't chatting to myself for a while. At least there was that. So I've had now 3 or 4 failed attempts at starting the stream, and I just started by being muted, which was my own fault. So no, none of my issues involve the cat. This is issues at Restream. I am not sure how long we will be up for. There is a chance that it might crash again. So yes, there is a chance that it might go down again. So let's see. Well, we'll do our best. And what I might do after this stream is actually delete the 3 or 4 attempts of the live stream, patch them together, and upload a complete version of this live stream. I normally don't do post-processing of my live streams. They're raw as they come. But given the technical issues, I might have to stitch something together. Just as a heads up, if the stream crashes again, I will not try to reboot it. This is the last try. If it crashes again, we call it a day, and I'll do the summary video at some point during the week instead. But let's see. I'm glad you all managed to migrate to the new link. I had to delete the old one and restart the whole thing. Let's see how this goes. I like the comment from David Howden here that if the sound doesn't work, I need to explain cosmology through interpretive dance. The good thing is I have the shirt for it. So I can just be like, space, stuff, space. We'll figure it out. Anyway, what I was just saying in the other stream before it cut off, and as I said, I'm going to attempt to stitch these things together at some point. What I currently work on is gravitational waves. Gravitational waves are ripples in the fabric of the cosmos, and they are produced by any object that is moving through the universe. So if you have anything like black holes smashing together, moving in a non-symmetrical way through the universe. So if you have things like black holes smashing together, if you have neutron stars smashing together, big black holes falling into small black holes, or even the universe itself in its infancy when it was growing, all of this can produce gravitational waves. Gravitational waves affect space-time. If they crash through you, they make you grow in one direction and then in another by a ridiculously small amount. I was just saying, let's hope my pen doesn't crash the stream again. If I have a measurement device, let's say I say this pen is 20 centimeters, it's quite hard to make measurements of something if the pen is also, or my measurement device is also going to change size when a gravitational wave comes through it. So if this is a gravitational wave, this is a measurement device, if a gravitational wave comes through it, it's going to grow and shrink, which means it's no longer a valuable measurement device. However, one thing we can use to measure gravitational waves is lasers. We know that light always travels at the speed of light, regardless of what it's doing, which means we know the precise timing of something. We can send lasers down a specific path, bounce them back and forth off of mirrors. And if something goes through and changes the distance between these mirrors, such as a gravitational wave, the arrival time of the laser beam is going to change. And by looking at the changes in the laser beam duration or arrival time, we can figure out if gravitational waves pass through the detector at any point during the observation. This is what we've already done from the ground. We've got amazing experiments called LIGO, Virgo, Calgary that are measuring gravitational waves from Earth. The next big step is to send the gravitational wave observatory to space. And this is where LISA, the Laser Interferometer Space Antenna, comes in. So LISA, the idea behind LISA is we would have 3 little satellites forming a perfect triangle, of course, an equilateral triangle, and these 3 spacecrafts will be chasing after the Earth as it orbits the Sun. These spacecrafts send laser beams back and forth between each other. As the laser beams go back and forth, they try to detect gravitational waves. Now, just to put this size-wise, when we work here on Earth, we have LIGO, we have Virgo. These have an arm length of about 4 kilometers. This is the path the laser goes down before it's recombined. These spacecrafts that are set to launch at some point will be separated by about 2.5 million kilometers, so substantially bigger than what we can do here on Earth. This is an idea of what it would look like. This is an artist's impression. Of course, you have these 3 satellites chasing around the Earth, orbiting around the Earth as it orbits around the sun. Sorry, not orbiting around the Earth, chasing the Earth as it orbits around the sun, sending laser beams back and forth between the 3 satellites. This is LISA, the Laser Interferometer Space Antenna. It is planned, it's a European Space Agency mission that is planned to launch next decade. So the news that we got in January this year, because this is updates of 2024, the big news we got in January 2024 is that the European Space Agency has formally adopted LISA. This means it's got the go-ahead. It is going to happen. It's on the schedule and the plan for the European Space Agency. It's no longer just a prototype. It's no longer just an idea. LISA is actually going to be funded by the European Space Agency. They have committed to it. So this is what is known as adoption. And the mission was formally adopted in January 2024, which is really good because a lot of us, myself included, have been working towards the LISA mission for a while now. And it's always a thing of like, is this actually going to go ahead? It had already passed the pre-approval phases, but as of January this year, the mission has now been formally adopted by the European Space Agency, which means it's definitely going to go ahead, which is pretty cool. And it was an exciting day for all of us involved in gravitational waves. Just to answer some quick questions, and just as a reminder, today's plan is recap of the highlights of this year. There are links in the YouTube video description to some of the past streams where I've gone into a lot of detail about these things. So I'm not going to go in a lot of detail today. It's just a recap. So I'll answer a couple of questions, but I'm not going to spend the whole hour and a half or however long talking purely about gravitational waves today. And one of the cats has just woken up and is looking hungry. They have food. He just wants his special evening food. So a couple of quick questions about gravitational waves. Question from Scott. I did see your question, but I didn't have time to answer it because the stream crashed. So are gravitational waves more intense nearer to the source? Not really. Yes and no. So gravitational waves diffuse in a spherical way, in the same way as light waves do. So while they are more intense closer to the source, the overall amplitude is expected to be the same. They will get diluted somewhat or dispersed as they spread throughout the universe. So it is more intense, but the overall effect is pretty similar. Follow comment from Abyssia. Speaking gravitational wave, were there reported neutron star merger after the one in 2017? There have not been. So in 2017, there was a very cool thing that LIGO detected 2 neutron stars smashing together. The advantage of having 2 neutron stars smashing together is you get a gravitational wave and an electromagnetic wave counterpart. So you get both. So because you get both, then you can use this as a cross-reference. We see the gravitational waves. We can also see the same events across the electromagnetic spectrum with a bunch of different ground-based telescopes and satellites. And this allows us to really get more information about the source of the gravitational waves and what happened. Hello, baby. Do you want to come up? One of the cats has realized that it's close to his dinner time. Hey, good day. Hello. No, now he's just going to stare at me. Yes. So lost track of what I was saying. Yes. So this event in 2017 where they detected neutron stars together allowed us to understand a lot of things about gravitational waves. We learned that gravitational waves travel at the speed of light. We learned the origin of a lot of solar system elements. But this has only been found once. LIGO has now been running since 2015, and we've only found one case of the 2 neutron stars smashing together. So it would be nice at some point to get more of these measurements, but for now we just have one of them. Going through the comments, a comment from Scott. You're not good at estimating length by eye, but is that pen really 20 centimeters? That's a good question. It's definitely more than 10. And I would say it's more than 15. That's my usual reference. So that is about 25, and the other cat's awake now as well. That is about 25. So yeah, I think 20 is probably a good estimate. Hello. So I now have both cats active because they normally get dinner at some point between now and the next hour, and they both just realized it's dinner time, and they were not fed before the stream started. So now I have one cat sat on my laptop, which is closed specifically because this cat likes sitting on it, and another one on the tower staring at me. Hello, baby. Are you going to sleep on my laptop again? Yes. Okay, I'm just going to show you the current status of my laptop. This is my laptop, and this is the cat. Sat on my laptop. So that's going to be. I've also locked the keyboard, the external keyboard, because he has a tendency to walk on the keyboard and turn things off. Hey, baby. Yeah, you're very sweet. You're a very sweet boy. This is Otto. Good is up there hiding. Or not hiding. He's up there staring at me. Okay. Hey, Paul. Thank you for stopping by. You might have seen there's 2 live stream links. There were some technical issues. We managed to figure it out. We're working on it. Hopefully this one will stay live. We've managed an additional 10 seconds to what we did last time. Do not bite the cables. This time, if there's a technical issue, it might be because there's a cat on my laptop investigating the cables, which is never a good thing. Do not eat the cables. Okay, comment from John here, question from John. Would a gravitational wave heat up a medium it passes through? It does not. A gravitational wave does not cause friction. Friction is what you need in order to... Hang on a minute. Scratch that. Yes, it would. Sort of. Yes, no. So technically, a gravitational wave itself does not produce heat or friction. So you need friction to have heat. Gravitational wave does not produce friction in that way. However, one of the early ways that people conceived of measuring gravitational waves, which actually to some degree worked, was having a kind of metal contraption with the idea that if a gravitational wave passed through it and it grew and shrank slightly, this and the metal itself would create friction, which would generate heat. So while the gravitational wave itself does not produce friction, if the gravitational wave acts on the specific objects, they can produce friction. So a gravitational wave itself does not heat up a medium, but it can induce an effect in something that would heat up the medium, if that makes sense. Okay. Yeah, cats love sitting on rectangles. I have no idea why. Like when I was building the cat tree, I had one piece of paper with instructions and I put it down and one of the cats sat on it. The other one tried to climb the cat tree as I was building it. They're very helpful cats. Okay, comment from Prathia. I'm going to move on from gravitational waves very quickly because there's like 10 things I want to talk about. Gravitational waves is just one of them. Question from Prath. Speaking of GW170817, can you please have one topic in a stream where you decode the gravitational wave, NGS, etc. code names? Yeah, astronomers and astrophysicists, cosmologists love using random acronyms. Usually for the gravitational waves, it's quite simple. There's the GW for gravitational wave, and then there's a date in the format of year, month, day of when it was detected. However, the NGC ones are then quite a lot harder to decode. So we can definitely go into that at some point. Like, here's all the acronyms that astronomers use and why none of us actually know what they mean. Question from John here. Is there a maximum distance that LIGO and LISA could detect mergers from? So it's not so much about the distance. What matters is the frequency of the gravitational waves. The frequency of the produced gravitational waves depends mainly on the source itself. So I'm just going to show you here this image that I flashed last week as well. There's a lot to unpack here. Don't worry about taking all of this image in. The idea here is at the top of the image, we have the sources of gravitational wave. At the bottom, we have the possible detection techniques. And in the middle, you can see this overall frequency thing. The idea here is that things like rotating neutron stars produce gravitational waves of a higher frequency, so to the right, whereas things like the early universe produces very small frequency gravitational waves, so to the left of this image. So you have this kind of shifting of gravitational waves. So LIGO and LISA and so on are sensitive to a specific frequency range, which depends primarily on the source, not on the distance to the source. Because as we mentioned before, what mainly affects the frequency and the wavelength of the gravitational waves is actually the source at the origin, and not so much how that has propagated towards us. Okay, so exciting thing number one that happened in 2024, LISA was formally adopted by the European Space Agency, which means it's going to happen. Currently, it's scheduled for launch in 2035. We will see how that actually goes. Second piece of news this year, which is kind of a sad but bittersweet piece of news, also in January, Ingenuity. So Ingenuity is a little baby helicopter that hitched a ride to Mars aboard the Perseverance rover in 2020. There was this big whole like Mars 2020 thing where NASA launched Perseverance, a little rover, and Ingenuity, a little baby helicopter. They went to Mars. They had a very successful landing, a very successful mission so far. So Ingenuity was this little helicopter that had the mission of testing if we could do any type of space, like operated space vehicles, space flight vehicles operated on Mars, but operated from Earth. So it was prototyping this whole concept of, can we fly things on Mars? You know, if we have a little helicopter there, can we fly it? So Ingenuity was initially planned to have 5 flights. It successfully completed 72 flights. It not only exceeded expectations, it smashed them out of the park. It saw that line and like ran past it. It was supposed to do 5 flights. It did 72. That is an incredible amount of flights. It got a lot of data about Mars. It helped Perseverance go in specific directions. Then on its 72nd mission, on its 72nd flight, it landed on its side, which meant the solar panels were no longer getting any sunlight, and so it was basically decommissioned. It's been left on the surface of Mars. This also happened in January this year. It's kind of a sad thing, but also it's amazing to consider that Ingenuity was only supposed to fly 5 times and it actually flew 72 times. That is an incredible achievement for the little baby helicopter. That also came out in January. So, first highlights of the year, Lisa got formally adopted, Ingenuity stopped working. I did a whole stream about these 2 things. Link is in the comment section down below. You're a very cute boy being a loaf on my laptop here. Yes, I am going to talk to my cats constantly throughout the stream because cat is here, cat wants attention. Question from David Howden here. Would gravitational waves be redshifted if moving? Yes, gravitational waves do get redshifted as they travel throughout the universe. And you also get some small Doppler effect of if the source is moving away from you. Okay. Yeah, cats do like sitting on little papers or boxes or anything you put down for them, really. They do like the carpet on the floor as well, although my laptop is apparently the best place to sit. Okay, so those were 2 things that happened very, very early on in the year that I talked about extensively. 2 other things I want to talk about briefly because there's like some main topics. Now I want to get into a couple of minor topics. There have also been a couple of really, really cool space launches this year, one in October and one in December. So the one in October was the Europa Clipper mission, a European Space Agency mission. And the purpose of Europa Clipper is to travel to Jupiter's moon, Europa, and to study the composition of this moon. So this is a moon that we think has a liquid core. It looks like the moon is made of ice, and it could have liquid oceans beneath the ice. So there's the rocky core, the ice on the surface, and in between these there could be oceans. Europa is one of the prime candidates of places within the solar system where we might find some type of microorganisms or some type of life forms, because Europa could have the right chemical composition. These oceans would be kept warm by geothermal energy, and they could have some type of nutrients. We have not yet found anything there, but the Europa Clipper mission is aiming to study the atmosphere, the properties, and the composition of Europa. The mission launched in October this year, and it is going to reach Jupiter in 2030. It is a long journey. It's going to take 6 years to get there, 5.5. Once it gets there, Europa Clipper is going to do 49 flybys of Europa. So it's going to be orbiting Jupiter, it's going to be orbiting Europa, and it's going to do 49 flybys where it gets really close to the moon and then flies off. By doing this, it can actually get some ideas of the properties of the composition of the moon. So Europa Clipper launched a couple of months ago. We won't get any more updates until a few years from now. It's also doing the cool thing where, the journey from here to Jupiter is a long one, and getting propulsion and fuel to make that journey is quite difficult. So a lot of these satellites, what they do is they have kind of gravitational slingshot maneuvers, where they use the gravitational pull of other planets to slingshot around and get sped up. This is something that they actually do in Armageddon. Armageddon, the classic Bruce Willis apocalyptic film, which has so many scientific flaws, let's not even go into it, actually does talk about this slingshot maneuver. And it's something that, one of the few things that you're like, that's actually not wrong. Also, if any of you here are Farscape fans, the slingshot maneuver is literally what John Crichton does to create the wormhole in the very first episode. If you have not seen Farscape, what are you waiting for? One of the best sci-fi shows out there. So, Europa Clipper is going to slingshot around Mars in 2 years and then shoot off towards Jupiter. It will reach Jupiter in 2030, and it will give us a lot of information about Jupiter's moons. There's also a mission going in parallel called JUICE, which launched last year. JUICE is a NASA mission, and these have very complementary objectives. They're both going to do flybys of different parts of the moon, so they will be able to share information. Europa Clipper launched in October this year. Keeping with space missions, there was a mission launched not that long ago, actually, basically 3 weeks ago. I just didn't mention it on the live stream because I was a bit distracted, but there was the Proba 3 launch. Actually, I did mention it in one stream at some point very briefly. The Proba 3 launch, or the Proba 3 mission, is a very cool concept. It's 2 satellites, and they are going to be one of the first to test synchronized flying. So formation flying, basically. If you've ever seen synchronized swimming, imagine doing that with spacecrafts, where you want them to move in exactly the right way at exactly the right time. So Proba 3 is going to have 2 missions. JUICE is an ESA mission. Thank you, David Dunn. Yes, JUICE is indeed a European Space Agency mission as well. Yes, as well as Europa Clipper. They are indeed European Space Agency missions. Yes. Okay, question about Europa Clipper, and then I carry on with Proba 3. Question from John here. Is Europa Clipper going to try to fly through a plume to test a sample of the water, or is that a different mission? I think the one that's trying to fly through a plume is actually JUICE. Europa Clipper is just going to do the flybys. It's not, I don't think it's planning on flying through any plumes specifically. So, Proba 3, the idea is there's 2 satellites. They're going to be very perfectly synchronized. They've launched together, then they're going to separate, and every couple of weeks they're supposed to come together and do a specific maneuver and then carry on, drift apart again, and then come together and do this maneuver and then drift apart again. The maneuver that they're doing is simulating a solar eclipse. So there's 2 satellites, one of them which is called the coronagraph and one of them which is called the occulter. Very nice names. The occulter is going to occult things. The coronagraph is going to try to measure the corona of the sun. So the idea is the occulting one, they're positioned 150 meters apart during this maneuver. The occulting one blocks out the light of the sun. The receiving one, the coronagraph, can then look at the corona of the sun to study basically what would happen during an eclipse. This is how one of the best ways to study the corona, or the outermost layer of the sun, because you can block out most of the light coming from the center. So Proba 3 is going to be mimicking solar eclipses on a small scale. One of them is going to block out the sun, the other is going to pick it up. Okay, yes, so I mix them up. Thank you for correcting me on that, David Dunn. So Europa Clipper is a NASA mission, JUICE is an ESA mission. I knew they had one each. I just wrote down the wrong information for both of those. Yes, Europa Clipper is NASA, Proba 3 is European Space Agency. That's what I mixed up. So yes, Europa Clipper is NASA, JUICE is ESA, European Space Agency. Similar objectives, very complementary. JUICE by ESA launched last year, Europa Clipper by NASA launched this year. Proba 3 is a European Space Agency mission. So they have these 2 satellites. They're going to perfectly synchronize. One is going to create an eclipse. The other is going to read the information of the eclipse, and then they drift apart. Now, studying eclipse is kind of a secondary objective. The main objective is the Proba 3 mission is to test this synchronized maneuver. And it's done in a way where all of the information is already uploaded. There will be no information sent from Earth, no guidance, no directions. These will not be operated from Earth. They have to operate autonomously. So the idea is they've already been given all of their maneuver instructions, and now we sit back and see if it worked. And it's pretty cool because this type of information is going to be really useful for future space missions that have to be at the perfect distance or that have to be kept in complete synchronization. This type of information that we'll get from Proba 3 will help with that. So that's also a very cool thing. Okay. So that's in terms of the space missions that I wanted to talk about. LISA's been adopted. Ingenuity stopped flying. Europa Clipper was launched in October. Proba 3 was launched in December. Been a pretty active year in terms of space missions and launches and stuff like that. But bringing it back to cosmology a bit, we've also had some major data releases from several different telescopes over the years. Over the year. And I'm distracted by my cat looking very cute here next to me. I just realized I have not drank any water in this stream. Remember to hydrate, people. Hydration is important. I have been told that I do publicity for Big Water by telling people to drink water. Anyway, so apart from apart from these cool space missions, we have had results from several major telescopes. Did I mess up the order of my things? Yes. So one of the first to release data this year was the Dark Energy Spectroscopic Instrument, DESI. This is what DESI looks like here. It is, it is a ground-based mission out in the Chilean desert, and the Dark Energy Spectroscopic Instrument is trying to map the universe. It's trying to create a detailed 3D map of the cosmos. So it's measuring galaxies, using different methods to get the distance to galaxies. Can use this information to create a 3D map of the cosmic web, of the structure of the universe around us. So just to give you an idea of what we expect to see, this here, when it comes up on screen, this is what the cosmic web looks like according to our simulations. Every glowing dot here represents a galaxy, and we expect these galaxies to form this kind of cosmic web structure, where you have places where you have a lot of matter, and you have places where you have not much matter, which are the cosmic voids. This is the cosmic web structure that we expect from our standard model of cosmology. This is what we get from all of our simulations. This simulation here is the Flamingo simulation. It is the biggest simulation we have been able to do of galaxies evolving under what we think are the laws of physics we've been able to observe in the universe. This is what we expect the cosmic web to look like. Until recently, one of the most detailed maps we had of the cosmic web was this one here from the Sloan Digital Sky Survey. It goes out to redshift of about 0.14, which is not too far back in time. It's looking at close by galaxies, but you can see here that every dot represents a galaxy, and it very, very closely mimics what we expected to see from the cosmic web simulations that we have done. Before I get into DESI results comments here, comment from Abyss: maneuvering command sent from Earth take a long time, so some level of autonomy in the probes is very important. Exactly. So one of the main things they're testing with Probe 3 is, can they get this synchronized high precision configurations without maneuvering it live? That is one of the things they want to test. Comment from Scorzio: hear me out. Okay, what if the two satellites develop sentience during their mission, fall in love, and decide to abandon the objective to fly off to explore the cosmos together? I feel like that is a plot line for an AO3 story. If you don't know what AO3 is, don't look it up. But yes, that feels like a plot line for an AO3 story. Please feel free to go write it. Please do not bother sending it to me. Have fun. If you want to write about spacecrafts getting up to stuff in the universe, be my guest. There are places for that online. I'm sure there is a market for that. Okay, so Dark Energy Spectroscopic Instrument started taking data a few years ago. Hello, fellow human savants. I love the greeting of hello humans. It's like, yes, hello, fellow humans. You are doing a very good job fitting in here. Well done. So Dark Energy Spectroscopic Instrument started taking data a few years ago, had some setbacks during pandemic and lockdown days, but this year, we got the first data release from Dark Energy Spectroscopic Instrument. It released the most detailed 3D map of the cosmos ever. I'm going to show you what it looks like as soon as the stream moves. This here is the amount, here is what DESI mapped. So it mapped almost 6 million galaxies in its first year of data. This is so much more than what we've done with any previous experiment, and it did this in its first year. So before I showed you, where was it? Go back one slide, this one. This is what we did of the Sloan Digital Sky Survey. Sorry, this one here. Sloan Digital Sky Survey. And just comparison with what we've done now with the Dark Energy Spectroscopic Instrument with DESI. You can see the full map in the background and then a zoomed in version of this little part here closest to us. Again, every dot in this map represents a galaxy. DESI has already mapped 6 million galaxies in its first year. This is an incredible amount of data. If you're wondering why it always looks like triangles like this, our galaxy lies at the center here, and we always look up or down, and across the band that has the Milky Way, we don't get as much information because the stars in the Milky Way block it out for us. But you can see here how many galaxies DESI has been able to map in its first year. This is an incredibly detailed map. This is an amazing way of seeing the universe. It's really, really, really cool. This was just after 1 year of data. Now, the cool thing is DISY actually already has 3 years of data. They've just only processed 1 year of data. So this was year one data, but they're already working on releasing data from year three, so from the first 3 years, which is expected to be even more precise and even more advanced. What's the scale difference between that DISY map and the Sloan map? So this goes out to redshift 6, sorry, to redshift 4. To redshift 4, the other one went out to redshift 0.14. Redshift is something that scales logarithmically, so it's not a linear increase in distance, it's a huge step in distance. DISY is peering back 10 billion years in cosmic evolution. It's going back so far in cosmic evolution. It's incredible. Thank you for stopping by, Breath. Happy New Year. Happy holidays. I'll see you next year. And if you can't find the replay, it's because I'll stitch things together at some point instead of having disjointed streams. Thank you for stopping by. So apart from this really, really, really cool map, DISY is not just making pretty pictures. It's also doing some very cool science. Now, one of the things that you can do with such a map is you can map cosmic structures. And by looking further and further away, you're looking further back in time because it takes a while for light to reach us. So this means that you can map cosmic structures today, and you can map how cosmic structures have changed over the history of the universe, which allows us to get some information about how dark energy is behaving. So just to recap here, because now I'm going to get into actual cosmology as soon as I find the right image. I got a new slide deck just for today, which means I don't know where any of my slides are. Where is the image that I want? Here it is. Okay, this is not the image that I want for once. So we know that the universe has three main components: everything you see, everything you're accustomed to, everything from me to my cute cats to my tea mug. This is normal matter. Normal matter only accounts for about 4.9% of the energy budget of the observable universe. There's a next 26.2% that is in the form of dark matter. Dark matter is this weird type of matter that interacts via the gravitational force, but it does not interact via the electromagnetic force, which means we cannot see dark matter. Dark matter does not reflect light, dark matter does not emit light, dark matter is basically invisible, which makes it very, very hard to detect. The remaining 68.9% is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that is pretty much everything we know about dark energy. One other thing we think we know about dark energy is that it's constant. Dark energy today is the same throughout cosmic evolution. Dark energy in the past behaves the same as it does today. This is something we think we know about dark energy. Where do we get these numbers from? Well, we get these numbers from the cosmic microwave background radiation. This thing here. This is a snapshot of what the universe looked like 380,000 years after the end of inflation. What you can see here are the particles of light that were produced in the very early universe as they broke away from everything else. The orange spots correspond to slightly warmer spots, slightly warmer photons or particles of light. The blue ones are slightly colder. Based on how many warm and cold photons we have and where they are distributed, we can get information on what the early universe looked like. Basically, we can use this to get, my slides are going in the wrong direction. We can use this to get these very, very, very precise numbers about the constituents of the universe. So what did DISY have to say about this? Well, after 1 year of data release, or 1 year of data analyzed in the first data release, DISY actually found hints or possibilities that dark energy changes throughout cosmic evolution, that dark energy behaves different today to what it did in the early universe, that dark energy is not in fact constant. If what DISY has found is correct, it challenges our standard model of cosmology. This picture of there's this amount of dark matter, this amount of dark energy, and so on. Our whole standard our picture of cosmic evolution is challenged by the DISY results. Now, the DISY people were very cautious in advertising and emphasizing the fact that this is 1 year of data. They will get a lot more precise data, and currently they're what we call between like 2 and 4 sigma away from the standard model of cosmology. Sigma is your degree of belief. Usually we only claim something as like a discovery if it's over 5 sigma. So the DISY people are being very cautious in not claiming a discovery. So far they've just said, we found something unexpected with dark energy. We'll know more as we get more data over the next few years. So DISY year one release happened in April this year. It was amazing. We got this picture of the universe. really incredible picture. And we got hints that there might be more problems with our standard model of cosmology, which is always fun. Again, I did a whole stream specifically about DESI. There's a link to it in the description down below. Question from John. Do you think the year 3 release will be precise enough to confirm evolving dark energy? Rumor is that it will be. I think the amount of galaxies they're going to get is going to increase. But what is also going to increase is some of these galaxies here, they only got one pass off. You can see there are some places where the dots look like they're missing something, especially in the background. You can see there's bands that appear to be cut out. So in the year 1 data release, because of the way that DESI scans the night sky, there are some galaxies that it only got one image of. As we get, ideally, DESI will sample every galaxy multiple times, which increases the precision. It reduces the chances of making mistakes. So one big change between year 1 and year 3 is a lot of these galaxies will be looked at the second or third time. So the precision is going to increase, which means our degree of belief in the DESI results is also going to increase. So while it's a bit hard to say for sure if year 3 data is going to be enough to verify their claims of time varying dark energy, it will definitely make the error bars on this measurement smaller, so it will make our degree of belief in the results higher. So it will definitely be very, very interesting and very revealing. Now, the cool thing is the analysis of year 3 data has already started, or the 3-year data release has already started, and it's expected in 2025 already. So people are already, because analyzing the year 1 data always takes the longest because it's when you need to test everything. But they already have the year 3 data and they are already analyzing it. So there's a high chance that we will get the year 3 release already in 2025, which is very cool and very exciting. So let's see if that happens. Okay. This happened in April this year. I did a whole stream about it, link down in the description below. Next cool thing that happened in cosmology this year, we got another data release from another experiment, one of my favorite space experiments. Okay, my cat is very clearly telling me that it is food time, and I have not yet fed them. They have food, they just want their special evening food. Yes, my cat is telling me that it's time for special evening food. We'll get it soon. Okay, so July last year, the European Space Agency launched Euclid. Euclid is an amazing mission that is set to measure dark matter and dark energy. They're calling it the Dark Explorer, or the Dark Detective, I think was the fancy name they came up with for it. Hello. Do you want to come up? You can come up again. You just got off the laptop if you want to come up again. Yes. Euclid is the Dark Energy Explorer, the Dark Energy Detective, a Dark Matter Detective, as they're calling it. And Euclid this is an artist's impression of what Euclid looks like. Euclid is going to take basically what DESI is doing on the ground, Euclid is going to do in space, but that means that it can stare more intently at specific galaxies. So instead of mapping the whole sky, it's going to get a very detailed map of specific patches of the sky. So it can stare very deeply into specific regions of the cosmos. So Euclid launched in July 2023, and in May 24, we got the first data release. Now, what they were calling it is a pre-release. Now, the pre-release does not contain any information about dark energy or dark matter. What it did contain is 5 papers about the telescope, about the performance in the first year, about how things were going, if things were doing what we expected in terms of the telescope. The other thing, together with these 5 telescope papers, were 5 papers about the pre-release projects. These were projects that had the objective of basically testing that everything was working well without doing the main goals of the Euclid mission, but doing some side quests, so to speak. So there were a bunch of proposals submitted, around 30 proposals. The European Space Agency selected a couple of them, and these are ones that use the pre-release data to do some amazing science that is not directly connected to the main objective of Euclid. The reason for this is they can use quick images, first images, to already do science. Some of this included studying exoplanets, studying star formation, things like this. So together with the 5 technical papers, there were 5 science papers about specific missions, specific side quests or things that Euclid looked at. And each one of these came with images. So we got the first 5 actual science images from Euclid already early on in December last year. We got the 5 kind of test images from Euclid where it was staring at stars and aligning and stuff. Now, the images that we got in May this year were actually the first science images. So we got 5 images from Euclid this year. Let's go through them very quickly. Again, I did a whole stream about this back in the day when it came out. These were the 5 images that were released the previous year. So these were the first December releases of Euclid. And then we got the ones that were actually released this year. So the new ones, let's go through them. First of all, we have, if it's going to load, this one here. This is a Bell 2390. This is a cluster of galaxies. And you can see here there's a huge amount of galaxies in this image. There's a bunch of stars, but there's also a huge amount of galaxies. So this is a Bell 2390. This is one of the 5 images that ESA released on behalf of Euclid this year. This is an amazing image. This is really staring at a patch of the sky. The mosaic image they released recently was gorgeous. Yeah, somehow I forgot to include that. Yes, thank you for that comment as well. Question from Lothario here. Will the Roman telescope overlap its capabilities with Euclid, add to it, synergize with it? Yes. The Nancy Grace Roman telescope is a NASA-based one that is going to have similar objectives to Euclid. It's going to stare at a slightly different region of the sky, and it's expected that their data will overlap in some regimes so they can cross-check each other, but they will also provide slightly different data sets. So they will be highly complementary and they will have a lot of synergy and they will work really well together. So it's absolutely important that we get both of these coming in together. Okay, so we had this image. Then we had the second image that came with this, which was this one here, Messier 78. This is the one that they used to study star formation. This is a region of the night sky that is producing stars. Very, very, very cool one. Then we also had, I'm just going through these quickly again. I did a whole stream about this. We had NGC 6744. It's in a very nice galaxy. It's a very pretty galaxy. It's quite close by to us. And by looking at this galaxy, we can understand things about how galaxies form. This was one of the first missions, one of these side quests that Euclid did. We also had, coming up now, a zoomed in version of a Bell. So this is the same as the first one, but zoomed in, focused on a very specific region. And what they're looking at here is how we can look at specific clusters of galaxies, which is very, very cool. And the 5th image that was released in May this year is this one here of Dorado, 2 galaxies that are very close together. This binary system of galaxies, very, very cool images. And then a couple of months ago, I think in November this year, we also got the mosaic image where Euclid released kind of its full sky map that it has so far, where it's not going in detail in a lot of places, but it's just kind of like gradually mapping out the night sky. I forgot to include it here, but that is also a very cool image. So takeaway here of this part is that Euclid has produced a huge amount of data already, and we haven't even got into the in-depth nitty-gritty cosmology and astrophysics data yet. This is the pre-release. Pretty pictures, some early science, just proving that Euclid is doing its job, it's working, things are going as planned, and we can expect to get some very cool results from Euclid. The first official data release of Euclid with some cosmology results, some dark matter, dark energy results, is expected in early 2025 already. So officially it might be delayed a bit, but in 2025 we'll get the next information from Euclid and the next information from DESI potentially, which is very, very cool. So big things have happened this year so far. That is not what I meant to do here. Big things that have happened this year so far in terms of results, DESI results, Euclid results, both of them very, very, very cool. Then we need to talk about the other big thing that's been happening this year, which is the JWST, the Just Wonderful Space Telescope. It was launched Christmas Day 2 years ago by now, 2 or 3 years ago. Launched a few years ago on Christmas Day. The JWST is advertised as kind of the successor to the Hubble Space Telescope. It looks at a slightly different frequency range, so they do have complementarity. but it's staring very intently at close by objects in the universe. So it's not so much interested in making a map of all the galaxies, but rather staring at specific things. The JWST has one of the things it's done is it's stared very precisely at different types of stars in close by galaxies. It's stared at supernovae, at Cepheids, tip of the red giant branch stars, and at carbon-rich stars. And this is very, very interesting because all of these stars can be used to measure the expansion rate of the universe. So we know that the universe is currently expanding and this expansion is accelerating, which means the universe is expanding faster today than it has been in the past. However, when we ask the question of how fast is the universe expanding, we get different answers depending on how we ask this question. There are different ways we can go about measuring the expansion rate of the universe. One of them is by using the CMB, the cosmic microwave background radiation, that map of the earliest light we have in the universe. By using that map, we can get an idea of the cosmological model, we can project it forward and figure out how fast the universe is expanding today. Another way, if we do this, you get a value of about 67. Another way you can go about measuring the expansion rate of the universe is using supernovae, which are stars that have reached the end of their lifetime and exploded. They produce a specific amount of light. By looking at how much light we get from these stars, we can figure out how far away they are. But this is usually done in a multi-step process because we need something to calibrate the supernova. The supernova are normally calibrated using what is known as Cepheid stars. Cepheid stars are stars that have a specific, they're basically like lighthouses. They have a specific brightness that has a specific period. So we can use this to get very accurate measurements to the distance. Up until now, anytime we've measured the Hubble rate using Cepheids and supernova, we do it using Cepheid data from the Hubble Space Telescope. If you do this, you get a value of the expansion rate of the universe of about 73. 67, 73 are not too far apart, but they're too far apart for comfort. We would ideally like them to be a lot closer than that. So this is what is known as the Hubble tension, the discrepancy we get in the Hubble constant depending on how we measure it, where the Hubble constant is the parameter that gives us the expansion rate of the universe. Now enter JWST. So over the summer, a group of people from the Chicago Carnegie Hubble program redid the supernova analysis using Cepheids calibrated on JWST data instead of Hubble Space Telescope data. And what they found is they actually find a value that is pretty close to the CMB value and pretty far away from the Hubble Space Telescope value. So it seems like JWST is not so much in agreement with the supernova measurements that we get using Hubble Space Telescope. I did a whole stream about that called Hubble Troubles, link in description. However, then the people who have always done the analysis on the Hubble Space Telescope data did the same analysis on JWST data. And they reached the conclusion that the results that these people obtained over the summer was heavily driven by the fact that they only had a few Cepheid stars, and if they had more, they would recover the same results as the Hubble Space Telescope. So basically, the JWST may or may not have new information about the Hubble constant, but it's still a highly, hotly debated topic. Comment from John here. If DISY does confirm revolving dark energy, would that affect the Hubble constant as derived from the CMB and lambda CDM? Yes, it would. Absolutely, it would. But in a way that doesn't help with the Hubble tension, because from DISY results currently, you actually find a lower value of the Hubble constant. So it shifts in the opposite direction. So if you consider that we have, CMB here 67, Cepheids and supernova 73, DISY is actually slightly shifted to this side. I can't remember the exact value, but it's slightly smaller than the 67, 70, 68 you get from CMB. It's slightly smaller. So if we have time revolving dark energy, it affects our value of the Hubble constant because the way we project this value forward from CMB times until today changes. But it doesn't actually solve the Hubble tension. In any case, it would make it slightly worse, which is very interesting. So yes, JWST may or may not say something about the Hubble Space Telescope. We're still not sure about that. It's still kind of like, So we'll see, I guess. I guess we'll see is the conclusion there. Okay. Something else JWST keeps doing is it keeps finding galaxies that are older than we expected. So we have our idea of cosmic evolution, of how structures form throughout the universe, at what time different things happen in the history of the universe. We think we have a pretty good understanding of this, but then JWST keeps finding galaxies that are older than what we expect. So back in July, JWST found galaxies that were formed 300 million years after the end of inflation, which is early days. It's very early days. And in December, there was another publication using JWST data where they found galaxies formed 600 million years after the end of inflation. Again, very early days. Now, all of this data right now is not conclusive enough. There have been papers saying that some of this could be dust clouding, where you have other things between us and these galaxies affecting the JWST measurements. So it is not convincing enough, but it keeps happening. It seems like JWST keeps finding galaxies that are perhaps not what we expected to find. It's still not conclusive. We still need more information in this regard. But when JWST launched, a lot of people in cosmology were saying, like, okay, yeah, it's going to do a lot of cool astrophysics and astronomy. It's not going to do so much in cosmology. But it might turn out that JWST questions our standard model of cosmology, which is very, very cool. So that's fun. So JWST may or may not shed new light on the Hubble tension. I did a whole stream about that. And JWST keeps finding things older than what we expected, and we still don't have a convincing explanation for that. So that is also cool. Final thing I wanted to mention that happened in 2024. Final thing, 2024. We have still not found dark matter. You know, this is, you'll know by now, the day we do find dark matter, I start my live stream with, hey, guess what? We found dark matter. We still have not found dark matter. Now, the thing is, dark matter in its most simplest form is kind of running out of hiding spots. So there's this general idea that we can measure two properties of dark matter using direct detection experiments where you build a massive detector and you hope that at some point dark matter just bumps into if enough dark matter particles go through your detector, at some point they will bump into something and produce a vibration and you'll be able to measure this. Usually to do this, you put specific noble gases in your detector, sorry, because then you get the specific properties that you're looking for. One of the most well-known ones is xenon. We have the xenon 6-ton experiment by now, which is 6 tons of xenon, just trying to measure any dark matter that's coming in. And it measures two main properties, the mass and the spin of the dark matter, and the coupling of the dark matter, so how much it's going to bump into these things as a function of the mass. And when you do this, you basically get a figure that's like, okay, if we don't measure anything, we exclude everything above a certain line. And then we go to the next one, we exclude everything above a certain line. As our detectors get more and more precise, this line gets lower and lower and lower, and we say everything above this line is excluded. So then the question is, how low can we go? And there actually is a lower limit, because at some point, our detectors are going to be so precise that they won't pick up just on dark matter if it's there. They will also pick up on a lot of other things, specifically neutrinos. So neutrinos are these super light particles that travel almost at the speed of light, that don't interact with much. They basically behave a lot like dark matter, except they move too quickly and there's not enough of them to be dark matter. But we know that the sun is constantly producing neutrinos. So there is what we call the neutrino floor. So as we move to lower and lower and lower interaction rates, we hit the point where we have the neutrino floor, where if our detector becomes more sensitive than that, we're no longer going to be finding dark matter, we're going to be finding the neutrino floor. So gradually over the last few years, we've pushed this line lower and lower and lower and lower. We're now at the point, as of this year, where we're starting to reach the neutrino floor. Both Xenon 6-ton and the Panda experiment, both dark matter direct detection experiments, both of these have reported the first hints of the neutrino floor. Now, once you hit the neutrino floor, it's very cool if we're measuring these neutrinos, but then we're not going to be able to find dark matter down there because we won't be able to tell it apart from these neutrinos. So as we push this lower and lower and lower, we expected dark matter to be somewhere at some point, and by now we've pushed it so low that is reaching the point where it's like, okay, we're almost at the neutrino floor and we still haven't found dark matter. And now Xenon 6-ton and Panda have both said, we've started to see what is probably the neutrino floor. So where is the dark matter? Of course you can change your properties of dark matter. Maybe they have a different coupling, maybe they have a different, there's a lot of different properties. Because we don't know much about dark matter, there's a lot you can change in dark matter in order to still be compatible with the lack of detection. But it's kind of like, would have been nice to have found it by now, but we keep pushing lower and lower. So another cool thing that happened over the summer this year is that Xenon 6-ton and Panda basically reached the neutrino floor, or almost reached the neutrino floor, in some mass ranges with some caveats, which is pretty cool, and still no dark matter. So where did it go? It doesn't mean we have to throw out our model yet, but it is a question of, okay, what do we do next? Where do we go from here? There's a lot of answers to that question. There's a lot of different ways we can look for dark matter. There's a lot of different types of dark matter we can look for. But the biggest direct detection experiments have not yet found dark matter. So, recap of stuff that happened this year. We've had a lot of cool stuff happen this year in cosmology and in science in general. Let's recap everything I wanted to talk about. Lisa, okay, before we go there. Comment from John: does hitting that floor make things like axions more likely? So axions are an alternative version of dark matter that you wouldn't find in these experiments, you would find in other experiments. Does it make them more likely? Probably not, but it does mean that we have to search for them, right? If we search for our main candidate and we can't find it, we have to consider every other possibility as well. Axions is something else, another type of dark matter. So the ones that I mentioned in this general picture were Xenon and Panda. This is what is known as WIMPs, weakly interacting massive particles, where you assume that there is some minimal interaction via the weak force that would enable us to find this. If you consider something like axions, they have a different formation mechanism and different search strategies. They're a different type of dark matter. So of course, if we don't find WIMPs, then we have to say, like, okay, where else should we look? People are already looking for axions as well. We also haven't found them. So, not finding WIMPs yet doesn't necessarily mean axions are more likely, but it means we still need to look for, all possibilities. We can't rule out WIMPs, so we can just say we still haven't found them yet. We keep searching, and eventually, maybe we'll get there. So, recap, quite a few things have happened this year in cosmology, in physics in general, but especially in cosmology. And the main ones I wanted to talk about: LISA has been formally adopted by the European Space Agency. It is go for launch in 10 years or so, 11 years or so, which is really, really, really cool. Ingenuity stopped working after performing a total of 72 out of 5 planned flights. Amazing. The NASA mission Europa Clipper has launched, heading to Jupiter to explore the moon of Jupiter called Europa, trying to figure out if there's any chance of life forms or microorganisms in the oceans under the frozen surface. Proba 3 launched, European Space Agency mission set to simulate eclipses, but mainly trying to figure out if we can do synchronized swimming with spacecrafts and how precise can we maneuver spacecrafts without giving direct commands, just letting them do their thing. We had first data releases from DESI and Euclid. We got amazing images of the cosmos. We got the most detailed map we have so far of the universe. And we found some hints in DESI data that maybe things are different to what we expected. We've also had more data from the JWST, which has found older galaxies than we expected and has potentially added a new direction into the Hubble tension, but that is still a matter of debate. And we still haven't found dark matter, despite many, many, many attempts to do so. So a lot has happened. But this also sets us up nicely for next year, because next year we should get more information from DESI, we should get more information from Euclid, we'll get more data from JWST, we might get more information on non-supernovae, which will help shed light into the Hubble tension. We're going to get a lot of cool things happening, and there's always space launches to be excited about. So yeah, there's going to be a lot of really, really cool things happening next year in cosmology. 2024 has been a great year for cosmology. I feel like 2024 has been the year where we've kind of gone, do we actually know do we actually know how things work in the universe? Are we sure we know how things work in the universe? Maybe we do. We hope we do, but maybe we don't. So there's a lot to be excited about. And there's a lot to look forward to next year in cosmology. And as always, if you want to stay up to date with everything happening in cosmology, subscribe to Cup of Cosmology and I will bring you the updates. Probably not live, but I will bring you frequent and live updates whenever I can about stuff happening in cosmology. Whew, okay, that is what I wanted to say in terms of cosmology. In terms of Cup of Cosmology, it's also been a great year. I know Cup of Cosmology has been a bit more inconsistent this year. I've had to take multiple breaks for health reasons and other reasons, but still, there's been quite a few streams. I think this year there have not been many guests because I've been focused on other things, but we have had some very cool streams. We've had a lot of regulars, a lot of new viewers. So thank you to everyone who's popped by. If you're here for your first stream, if you're here 9 years into this journey with me, thank you. Because Cup of Cosmology only works with you coming and asking questions. Otherwise, it loses its point. So the fact that you all still come in and ask questions 9 years into the show means so much to me. So thank you, everybody, for everyone who's come in and asked questions, like the videos, comment, subscribe. Those of you who support me on Ko-fi, thank you. Really, it means a huge amount to me. I know some of you support me very frequently. Some of you support me whenever you can. However much you do or don't support on Ko-fi, thank you. There's always a link in the streams. If you ever want to buy me a coffee, there's a link. Thank you to those of you who have. To those of you who have sent me emails and messages and just reached out, I really appreciate it. I don't always reply to your emails. I don't reply quickly, but I read them and I enjoy them. And I really do appreciate how engaged you all are. It really means a lot to me. So thank you for that. And for those of you who have asked super complex questions that I've had to go to my colleagues and have triggered week-long debate, that's also very cool. Thank you. Thank you for that. Okay, so I know we had some technical issues today. What I'm actually going to do is I'm going to delete the first stream, the 10-minute one that didn't work, and I'm just going to keep this one. I did enough of an introduction. There were some technical gremlins at the beginning, but I realized I don't want to go through the effort of downloading and stitching the streams together and re-uploading them, because then I lose a link. And I think one of the things I've always tried to do about Cup of Cosmology is it's unprocessed, it's live, it's interactive, it's not a highly fine-tuned, high-definition production value thing. It's just me chatting to you all about science, and sometimes there are technical gremlins. So I'm just going to leave this stream up as is. I'll delete the 10-minute one and just leave this one up as is. And we'll go with that. And now I should go feed my cats because they are very much telling me that it is food time. They have food. They just want different food. Yes, I'm talking about you. Hello, baby. Cute boy. Okay, so thank you, everyone who's been here throughout this year. It's been a great year for many reasons. In space, in my own personal life, in Cup of Cosmology, it's been a good year for a lot of reasons. We're going to have a great 2025. There's going to be a lot more science happening, a lot more cosmology happening. I've got a bunch of guests in mind who I will bring on next year. So you can expect a lot of cool stuff happening. Now, as I mentioned, this is the last stream of the year. There will not be a Cup of Cosmology next week. Cup of Cosmology will be back in the new year. Oh, big stretch. Good boy, big stretch. Cup of Cosmology will be back in the new year. You're welcome to follow me there. You know where to find me. Usual time, usual place, cupofcosmology.com for all the info. You can reach out at contact@cupofcosmology.com. And now I hope you all take a break, have a restful holiday, however you're spending it. Have a warm and happy welcome into the new year. So thank you everyone for being here throughout the whole year today and putting up with the technical issues, the chaos, me randomly talking to my cats. Thank you for being here and for all of the support. Really appreciate it. Cup of Cosmology will be back in 2025. I'm not yet sure when the first stream will be, but it will be in January 2025 on a Sunday at the usual time. I hope to see you all then. And I hope in the meantime, you will take care of each other and stay curious.